Assalamualaikum and hi everyone. This is pre-recorded video 14 for chemical bonding. In the previous video, we asked EPR part 2. We have done some exercises on how to predict the geometrical shape of a molecule. This is we asked EPR video part 3, and first we are going to discuss what happens to a geometry of a molecule when there are more than one central atom. For example, this acetic acid or ethanoic acid. To answer this question, we have to first determine the molecular geometry for each central atom. Let's do this. We assume the carbon on the left is the first central atom, which is this one. Okay, wait. Okay, this is the first carbon atom. Sorry, the first central atom. And this is the second central atom, and the oxygen here is the third one. Okay, so because these are the central atom, so the first carbon has the AX4 electron arrangements. This one, the first one, has AX4 electron arrangements, hence the tetrahedral geometry. Okay, the domain geometry, remember, electron domain. The second one has the AX3. Why AX3? 1, 2, 3, right? So electron arrangements, there is no a lone pair, right? So it has a trigonal planar geometry. And the third oxygen has the AX2, E2, AX2, E, two lone pairs rows. So the arrangements is a band geometry. Therefore, this is a 3D image of acetic acid with three different geometries which are tetrahedral, okay, for the first carbon. The second one is trigonal. The third one is band. Time for some exercises. Okay, so determine the shape around each central atom and predict any deviations from ideal bond angles in acetone and this molecule. You can check the answer with your lecturer later. This is another subtopic but related to the molecular geometry of a molecule. It's the polarity of molecule and the relationship with electronegativity. It is very easy to determine the polarity of a molecule by knowing the difference in electronegativity between two atoms. However, not all molecules that contain polar bond is polar. For example, the bond dipoles in carbon dioxide cancel each other because CO2 is linear. Okay, so this is polar, and this is also polar. The CO and CO here polar. The however it cancel each other because the amount of polarity to left and right are the same. Let's discuss the molecule of water here. We know that the molecular shape of water is band, so the molecule is not linear and bond dipoles do not cancel each other. Therefore, water molecule is a polar molecule. You can see the uneven clouds of electrons in oxygen is much condensed compared to the hydrogen part. Okay, you can see here the red part. If we understand the basic polarity of a molecule, then we simply can identify the polarity of this molecule. For example, HCl is polar because electron cloud attracted more towards Cl, with it shown by the polarity arrow here, HCl. Next is Bf3 is nonpolar. Okay, so Bf3 is nonpolar. Why? Because it's symmetrical. The molecule is symmetrical and the bond polarity cancel each other. Same goes with tetrachloromethane. Here, it's non-polar. However, for ammonia and CH3Cl is polar because of uneven contribution or distribution of electrons in the molecules. Before we end, please do this exercise of predicting whether the molecule is polar or not, and you can check your answer with your lecturer. That's the end for VSPR topic. Thank you. See you in the next video, next topic.